Right. It's time for us to start the lecture. It's 11:30. So we have already start on the first set of lecture notes. But before we actually go back to the lecture materials, there are some announcements that I would like to make related to this subject of Physics 1. The first one is that we have apart from the usual lecture hours, we should be having additional support for you all. The first one is the consultation hours, which are available if you go back either to the context on the Learn at PolyU. This is my consultation hours. During the consultation hours, you could go to the Zoom link and seek help from me without making previous appointment. If you have questions, of course, you could try to catch me either on the office phone number, or you can send me the email. And the consultation hours are at here for you to contact me without making any previous appointment, because I may from time to time disappear from my office for some other business. So that is the first thing. The announcements would have the details concerned with the consultation sessions. So you just have to click in the link and then go to the consultation session. And if you are too shy to ask me questions directly, you could also use another facility available on the internet, and that is the Physics Help Desk, which is available all the time. You just have to scan the QR code. Once again, it is on the announcement, so you just have to go to the announcement and follow the information. Leave the message on the inbox, and sometime within that day, some of our senior students would answer your questions. So that would be another way for you to address the questions you have in the Physics 1 lessons. The idea of the Physics Help Desk is to help you to address the questions. It is not going to solve the problems for you. So for example, if you have a problem in assignment and you ask what is the solution, I'm afraid they would not do it for you. They would tell you the directions, and that is it. So try to make the best use of these facilities in order to help your learning. And apparently, I can see a lot of your classmates in this subject that are joining as guests. So the idea is that rather than joining by means of the rather than joining the session by means of the meeting ID and the password, it is the best for you to come to the Learn at PolyU and click on the link. From here, you could join the session, I think, directly without going through the waiting room. Sometimes it may ask you to show something like the giving the username and password. Before you give the username and password, the first thing you should try to do is to click on the right-hand corner, and there is asking you for the SSO. Type in PolyU before you type your username and net ID and password. In that case, you will be logging in as some members in PolyU and do not have to go through the waiting room. It is not only inconvenient for you, it is probably inconvenient for me as well, because I have to click the admit attendees from time to time. So hopefully next time you could try to log in using the Blackboard entry link. Right. Without further ado, we would come back to the lesson. we have, as I've said, started the lecture set number 1. We have a very tight schedule, but we are hopefully in good progress. The first set of lecture notes, they are concerned with the linear mechanics. Most of the topics you have learned it from your high school teaching. So I would be mainly going through the revision of the topics, but sometimes there are issues that you would like me to address further, and I will spend some time on that. In the first lesson, we have gone through basically units 2 to 4, and also probably half of the unit 5. Just a brief recap, what we have seen in the lecture notes 2 and lecture notes 4, chapters 2 and 4, they are related to the kinematics. Remember what I mentioned about the study of the linear mechanics? Actually, the trend is like this. It is the same as what you have done in the high school, but the teacher might not have explained why it is the case. Just like when you learn something, you would first make observations, and the observations helps you to describe the behavior of a system and even to predict what happens to the system. And that is the idea of the kinematics. So you have the kinematics equations that helps you to predict what happens when you have an object that is undergoing constant acceleration motion. So these equations helps you to predict the behavior of the object. And if it is just one-dimensional case, it is very limited in solving physics problems. So we would have to sometimes consider motion in 2 dimensions. And that is the case of the projectile motion in particular. We resolved the motion into 2 components. And with that, we are able to consider them as independent and then resolve the equations separately. Yet, they are connected, of course, because the time of motion would be the same for the projectile motion. So they will be connected somehow by means of the time of flight. There are some equations in the lecture notes. Some of the important equations, they would be provided to you during the examination. So do not try to memorize the equations. The best you should do is to understand the concepts. And these equations, they could somehow be derived if you know the concepts. So, and actually, if you just memorize the equations, when the situation changes slightly, you would fall into the traps, and then you cannot solve the problems. We have seen some of the cases in the lecture notes when we have the projectile motion that does not fall on the same horizontal level. So in that case, the equations at here will not work. They are for the height of the flight as well as the range of the flight when you start from the ground level and then the projectile ends up at the ground level as well. So sometimes going back to the first principles is necessary. And we have also talked about the Newton's laws of motion. Hopefully, this would be just a revision for you. Although, from some experience, many of the students after the summer holiday, well, they have forgotten most of the stuff. But here is just a revision. The first law is concerned with the concept of inertia. And in the absence of any external net force, objects would remain in its resting state or linear motion with a constant velocity. When you have a force, then it would cause an acceleration. How quickly the object accelerates depends on the inertia of the object, and the measurement of inertia in a linear motion is mass. So the mass is an intrinsic property of an object, and it is related to how reluctant the object is towards motion, towards linear motion, to be more precise. Sorry, I think I may have to. Right, I cannot find here. Yep, sorry. So at here, you have also the Newton's third law, which is the concept of the action and reaction force. That is a concept of the internal force. When the forces are generated internally, they would be equal in size but opposite in direction. So if you have an internal force, if you like, they would cancel one another when you consider a large enough system. So for example, if you have a table and a computer, the computer would provide an action force by pressing on the table. And at the same time, the table surface will provide a reaction force. So it will stop the table from falling down. So there is an action and reaction force. So these are something you have probably learned before. And to solve the problems of the linear mechanics, you can apply the same trick that we have seen before. Try to separate the motion into different directions. Probably the motions should be separated in perpendicular directions, so they would not be influencing one another. And at here, we just would take a look at a couple of examples, which I would say they serve as a summary on what you have learned before, but they would be good to give you some idea what is expected from you when we talk about Newton's laws. Here you have a car that is parked somehow on a icy surface. So when you have an icy surface, you expect it to be smooth. There is no frictional force between the wheels and the road surface. So you expect the car to slide down, even you break it. And in order to solve this problem, say find the acceleration of the car and the car's speed when it arrives at the bottom of the road. So you have to apply Newton's laws. And here, when you apply the Newton's laws, it is always advisable for you to draw the free body diagram. The free body diagram, like the one shown on the right-hand side of the slide. So at here, you have the free body diagram. And forces acting on the car, for example, they are, of course, you have the weight of the car that pulls the car downward due to gravity, due to acceleration due to gravity. And then you have the surface that supports the car, otherwise it falls through the ground level. So originally, there should be two forces only acting on the car. You do not have friction because it is a smooth road surface. So you have the normal force and the weight of the car. Now, they are pointing in different directions because the road is a slope. You should try to resolve the forces into components such that you could apply the Newton's law to solve the question. You try to make the best use of the geometry other than making fun of yourselves. If you resolve the forces in the vertical and horizontal direction, then it is not very helpful. In this particular example, we would resolve the forces parallel to the slope and perpendicular to the slope. So when it is parallel to the slope, you would expect there is the component of the weight that accelerates the car down the slope. So mg sine theta, that is equal to ma, that accelerates the car down the slope. And what about along the direction perpendicular to the slope? You would not expect the car to sink into the ground or float into the air. So there should not be any acceleration in the y direction. Y refers to perpendicular to the slope. So normal force is equal to the weight component of the car perpendicular to the slope. So that is why we have this equation. And in this case, we could solve what is acceleration along the x direction. And then the next part is to, let me see, find the time, how long does it take for the front bumper to reach the bottom of the hill. So if the hill has a length, well, if the slope has a length of d, then you have the equation d equals to 1/2 at squared. Of course, you should have also v times t as well, but the car is initially at rest. So according to the kinematic equation, v is initially 0. The initial velocity is 0 for the car. So this is kinematic equation is for constant acceleration along the slope. So you could solve for t, and you could also apply the next kinematic equation, v squared minus u squared equals to 2as. Well, this is in the equation list, so you could apply it by taking use of the fact that initial velocity 0 and the length of the slope is d, so you could solve the problem. So hopefully this one is quite straightforward. And some of your classmates asked about the revision of weight of an object when it is accelerating downward or upward. So in this example, we try to weight a fish when it is hung from a balance inside the lift. Or of course, when it is at rest, when the fish is at rest, or when the lift is at rest, the tension in the string should be equal to the weight of the fish. So that is the normal scenario. And if there is any net force that would accelerate the fish upward or accelerate the fish downward, then the tension in the string that hangs the fish would not be equal to the weight. Whether the net force is pointing upward or downward depends on whether the system is accelerating upward or downward. If it is accelerating upward, you expect the tension to be larger than the weight. On the other hand, if the system is accelerating downward, then according to F equals to ma, the weight should be larger than the tension. So that is the idea. First, we consider the situation when the elevator accelerates upward. So if it is accelerating upward, then you would have T equals to ma plus mg. And so that would give you the tension in the string when it is accelerating upward. I think here we are missing the equation for accelerating downward. So if you try to consider the situation when it is accelerating downward, it is just the opposite. And maybe I should actually show the PowerPoint slide just to would you please actually turn on the microphone so I could be the only one speaking for the time being. Yeah, thank you. So I go to page. Right. So here, let's go back. Okay. Right. So, yep. For this equation, actually, you could use it to solve both upward and downward motion. The fact is, we are taking upward direction as positive. We are taking upward direction as positive. And that is why you have minus mg. So if A is positive, it is accelerating upward. If A is negative, then it is accelerating downward. So the tension would change accordingly. And now we have a realistic scenario such that the fish has an actual weight of 40 Newton and it is accelerating upward. Well, it is accelerating either upward at 2 meters per second square or accelerating downward at 2 meters per second square. So that is why you have plus and minus sign at here. And we are trying to figure out the weight as measured by the balance. And the weight measured by the balance is reflected from the tension in the string. So this is why you have two different values when the fish is measured with the lift accelerating up 48.2 Newton, or when the lift is accelerating down, that measures a weight of 31 Newton. Identically, you could replace this balance by the one that is sitting underneath the fish. The idea is the fish would be supported by the normal force from the balance rather than supported by the tension in the string. So the physics situation is actually the same. Either it is being hung by the string or being supported by a balance underneath the fish. So you could, of course, put the person on a balance rather than hanging the person by a string. And that would be a more humane situation to measure the weight of a person. But the situation would be identical. Now, of course, if you go back to this equation, you would find that when the downward acceleration is equal to g, that means the fish or the person including would be supported by zero tension. When you have a zero tension, that means the person is under free fall. So that would be the sensation of weightlessness, as you will see in your lecture slides. So if the cable suddenly breaks and the whole system is accelerating downward at the value equals to the gravitational acceleration. So the tension will be zero and it is a weightless sensation. Okay. Now, let us come to another point. And that is something also asked by many of your classmates. Well, okay, maybe this example first, because this example comes quite often in your assignment as well as in your quiz as well. Two objects supported by strings and connected over a pulley. The two systems, they are connected together in terms of the force because you have the tension in the string. In particular, if you have the string tension that is identical. When you have a smooth pulley, for example, there is no frictional force acting on the string, so the tension in the string, they would be identical. And another issue is when you have the objects connected by an string, that means they would be connected in terms of motion. When one object accelerates or moves upward by a certain amount, the next object would be falling instead by the same amount. Although the directions are different, the quantities of motion would be the same. The values would be the same, but the direction would be opposite in this case. So that is why you could connect the two systems. For example, on the left-hand side, you have the free body diagram drawn at here, tension, weight, and it is presumably accelerating upward. So tension minus M1G equals to M1A. That is for the upward motion of the left-hand object. And then on the right-hand side, you have the downward motion. You could write T minus M2G equals to minus M2AY, or if you take the minus sign, then it will be identical. M2G minus T equals to M2AY. So with these two equations, we are able to solve for the acceleration and the tension in the string. That is another typical type of a question you would encounter in the assignment, for example. Now, this topic, I have seen quite a lot of requests from the classmates, and I would try to explain a little bit details at here. In the previous examples, we have been talking about motion of objects on smooth surfaces, but in the real life, smooth surfaces seldom exist, and there are many situations when we encounter surfaces that are rough. The rough surface would have an impact on the motion because they would provide frictional force to stop or impede the motion. They will try to give some resistance to the motion, if you like. And what the people have found is that this frictional force depends on the normal force acting on the object. Now, what does it mean? Basically, you could try to verify it by doing a very simple experiment. You try to hold an object against the wall. So let me try if I can show this. You try to hold an object against the wall. Say this is the wall surface, and you try to hold the object against the wall surface. If the force that you push the object towards the wall, the force that you push the object towards the wall is large, and you try to move it up or down, you are making fun of yourself. You are making a joke of yourself because the frictional force in that situation would be large. So it is very hard for you to pull or for you to move the object up or down, or actually in any direction, when you push the object very hard towards the surface. On the other hand, if you just touch it lightly, and if the force is not large enough, then, well, I don't want to do it because I don't want to drop my mouse. If your pushing is not hard enough, then the object will start to move or slide downward. So this is not anything related to the grip. Of course, I have to grip the mouse in order not to have it falling down. But you could always take a book, use a finger, press the book on the wall, and then see if you press it very hard, whether you could move it easily up or down, or actually sideways. The frictional force is playing an important role in this situation. And the idea is the stronger is the push towards the wall, and the greater would be the frictional force. So if we translate this push into something that is actually corresponding to the normal force or the reaction force, if you like, acting on the object. So this normal force is determining the size of the frictional force, and they are proportional to one another. So we could write something like this. Frictional force is kind of equal to, now note the word kind of equal to. Frictional force is kind of equal to the normal force times a coefficient. They are proportional to one another. Now, actually, the situation is much more complicated than that. And we have to look at it into greater details. Say, we try to investigate the impact of the frictional force towards the motion of an object, like the one shown at here. When we are trying to, well, this is just a normal rubbish bin resting on the ground. So this is the force diagram for the rubbish bin resting on the ground surface. You have the normal force that is equal to the weight. That is something you would fully expect, because in the vertical direction, no other forces are present. And horizontally, if you try to pull the rubbish bin or push the rubbish bin by a very weak force, initially you will not succeed. You just touch it very slightly. You just try to touch it very slightly. It would not move. And then you keep on pushing with larger and larger force. It still does not move at the beginning. So what does that mean? That means you have zero net force in the horizontal direction, but you are pushing. So there must be some force balancing your pushing force. Your pushing force is F. So the balancing force must be the friction. Now, it comes to an interesting observation. Frictional force is not constant when the object is not moving. It is not a constant when the object is not moving. So it depends on how strong you push. If the object is not moving, once again, if the object is not moving, the frictional force is equal to the external applied force. So that is why you will see in what we call a static region, the object is not moving, the frictional force is equal to the external force. And of course, eventually, when you push it hard enough, it should start to move. This would be what we call the static friction. And that is the maximum frictional force provided between the object and the surface. So this maximum static friction is proportional to the normal force. And the proportionality constant, we write it as mu s, the coefficient of static friction. Now, once again, we have an object resting on a surface. We have an object resting on a surface. We try to push it. If you push it with a very small force, it does not move. If you push it harder, it still resists the motion. And because there is no change of motion in the horizontal direction, we conclude that the net force in the horizontal direction is 0. And that is why the frictional force, static frictional force, is equal to the external force. This equilibrium would break. This situation would break when you apply the force large enough to overcome the maximum static friction. This maximum static friction is proportional to the normal force. And the proportionality constant is mu s. So the situation is shown at here. This region is when the object is not moving. So when you push it over the edge, over the breaking point, it will start to move. Once it starts to move, then the situation is quite different. Once it starts moving, then the object would start to, well, accelerate because your external force keeps increasing. And the frictional force between the surface and the object after it starts moving would become a constant value. This constant frictional force is what we call a kinetic friction. This is a kinetic frictional force because you have relative motion between the object and the surface. You have the relative motion between the object and the surface. And in this situation, the frictional force would be the kinetic friction. And the kinetic friction is still proportional to the normal force. But the proportionality constant is changed. It is mu k. In real life, actually, mu s is larger than mu k. So the maximum static friction is larger than the kinetic friction. The maximum static friction, I'm saying the maximum, it is larger than the kinetic friction. So this is the situation for the frictional force. To make a brief summary, the frictional force is related to the relative motion between the object and the surface. The maximum static friction is the maximum frictional force that prevents the object from moving. Once the object starts to move, then due to the relative motion between the object and the surface, there would be a frictional force that is called a kinetic friction. Why is there an inequality sign? Because at here, you could see that the static friction, when the object is not yet moving, it could be 0. If your external force is not applied, there is no frictional force. If you start to apply a little bit of force, the frictional force is just enough to balance the external force. So frictional force could be small, could be large, and the maximum is proportional to the normal force. And that is why you have this inequality sign. Okay. What would be the point called when collide? Well, it is, well, if you like, it can be called a critical point. But of course, over this critical point, you would be changing from static behavior into kinetic behavior. So in many situations, you will be asked, what is the maximum force that should be, what is the minimum force that need to be applied in order to break the motion, or what is the force that should be applied to keep the object at least to move in a constant speed and so on. So this would be the kinetic friction and the static friction. Okay. So let us try to understand the situation by take a look at one or two examples. So let's try to take a look at this one first. So now you have an hockey puck on a smooth surface, a frozen pond, or is it? No, it's not. Well, it's not saying that it is smooth. And in any case, if the puck is always remain on the ice and slides 115 meters before it comes to rest, determine the coefficient of kinetic friction between the puck and the ice surface. Now, the idea is like this. The idea is like this. You have a surface. I would address the questions a little bit later. So I would answer the, I would explain the example first. You have a surface and then the puck is moving forward, and the friction is always in the direction opposite to relative motion. This is actually a very important point. You have relative motion between the two surfaces, the object surface and the ground surface. And so when the object is moving forward, you have the friction that is in the opposite direction. And because the object is moving, the surface friction is in a backward direction. Well, if the object is moving forward, the frictional force is in the backward direction. So in this example, you have the kinetic friction. And because you are just given the puck an initial push, in the rest of the motion, there is no other force apart from the frictional force that acts on the puck. So this would be the only force, and this force would decelerate the object. So in the vertical direction, for example, you have normal force, you have the weight, they will cancel. In the horizontal direction, you have the frictional force equals to ma. And this frictional force is equal to mu k times n, because that is the kinetic friction. N is equal to mg, and therefore you could solve what is the acceleration of the puck. And with this acceleration, we could calculate what is the distance traveled. So once we know the distance traveled, which is 115 meters, and then we put it into the equation, we could solve for the kinetic friction. So all the things are following quite nicely in the calculation. You just have to connect the two situations. First, the acceleration of the object, which is due to the frictional force. You say this is deceleration, that is okay, because it is just an acceleration in the negative direction. And you then connect the force to the kinematics. So you decide what is the equation to use to determine the motion of the puck. So in this way, you solve for the problem. Now, I come back to the question. So is it, if we do questions related to object, we must just take the minus of the kinetic friction? Well, you could assign the direction of the force. So it depends on how you draw the arrows. So I would not be giving you exact equations, whether it's a plus sign or minus sign. As long as you could adjust the directions mentally, in a certain sense, then you would be able to get the right equation. In here, in this example in particular, the positive x direction is from left to right. So that is why you have the frictional force, which is minus Fk. Here, the minus sign addresses the direction, and Fk is the value, if you like. If you go back to the equations at here, it does not tell you what is the direction. It does not give you a sign. It just gives you the magnitude. So that is why you have to give the sign by situation consideration, by considering the actual situation. So that is the question from Chen Junho. Okay. How could the, well, next question from Mr. Malek, I think. How could the coefficient of friction be greater than 1? It sounds a little bit strange, but it really depends. It depends on many different situations. For example, if you have some glue that is stuck on the surface, you have a piece of glue that is stuck on the table surface, and you try to move that piece of glue. Now, you would say, okay, that might be cheating because you have some chemical reactions between the surface and the glue. But in any case, if you try to move it in a horizontal direction, then what happens is you are providing some kind of a frictional force. The frictional force is the force that prevents the motion. So that is one of the possible scenario. Say at here, the rubber on concrete or steel on steel, it depends a lot on the finishing. It depends a lot on the finishing. If you have a perfectly flat surface, say a flat piece of steel on a flat piece of steel, the frictional force, well, depends on whether you have oil or not. The frictional force may be quite small. But on the other hand, if you have a carpet sitting on a ground surface, you try to pull the carpet on the ground, you will find that it is extremely tough. So it depends a lot on the finishing. So in a certain sense, these are not absolutely universal. Whether you have a finishing that is very smooth or a finishing very rough would make a lot of difference. And so if you have an extremely rough surface, then the movement would be very hard. If somehow the surfaces are very sticky, then it would make it even harder for the motion. That is why you have the say the small animal called a gecko that could actually have the feet that can help them to climb on the wall surface, because you have a very sticky feet. So the coefficient of friction, it is a measurement of the size of the frictional force. It can be quite large. It can be quite large, depending on the finishing and depending on the interaction between the object and the surface. Okay. Now, one thing I should remind you is that the frictional force is the force present that is opposite to the relative motion of the surfaces. When you have objects that are moving relative with one another, when you have the two surfaces moving relative to one another, you would have friction. But you should consider the frictional force the direction of the frictional force that is opposite to the relative motion of the surfaces. Think about a situation. You have a wheel that is rotating like this. Wow, sorry, that is not the best wheel I could draw, but hopefully you understand. You have a wheel that is rotating like this, and you try to drop the wheel gradually onto a road. So what would happen? When you have the road surface, it would provide the frictional force. But what is the direction of the frictional force? The point of contact between the wheel and the road surface, they are here and here. At the point of contact, the wheel is moving in this direction. Although, if you think about it, when you have the wheel rolling like this, it should actually be moving like that. So, the frictional force, because of the relative motion, it should actually be pointing forward. It is a kind of a counterintuitive, but you have a rolling wheel dropping on the road surface, you have the frictional force actually pointing forward rather than backward. Although at the end, the wheel is moving forward. So you see, you are not just considering the motion of the object, kind of like the case of a walking. Okay. So if you have the walking, you are trying to push backward. You are trying to push backward, and then the force would help you to move forward. So you should consider the relative motion of the surfaces rather than the relative motion of the object itself. Okay, so this is an special situation. Okay. Right. I would say time flies, and actually we do not have a time to go through the next example, but let me see. In this way, we have talked about the explanation of the static and the kinetic friction. You could go back to the lecture notes and see if the example would make any sense. In the situation at here, it is also the motion of the two objects connected by the same string. So the tension is the same. The only difference is that now M2 is moving on a rough surface. So you have the additional horizontal force that tries to stop the motion. Right. Just before you leave, I should give you some bad news. And that is your first assignment, which is now available. Well, actually at 12:30, it will become available to you at 12:30. So you could check the announcement and it would be released to you, the first assignment. The first assignment would be covering the kinematics. It will be covering the kinematics. So chapters from 2 to 4. And you would have around 10 short questions. You will be given 1 week to finish the questions. So please finish the questions on time. They will be done directly on the Learn at PolyU. So just follow the instructions on the Learn at PolyU to see the how it should be done. And concerning the content in the Learn at PolyU, I have also put up some tutorial questions. So some tutorial questions are already available for you. So at here, you could see that these are the tutorial questions from chapters 2 to 5, so up to Newton's law and friction. So please try to test your knowledge by working on the questions. Time permitting, I will be working on 1 or 2 of these questions, but solutions will be provided for you, so you could always go back to the solutions for how to solve the problems. And actually, we have some videos that have been prepared to work out the tutorial questions. And of course, I would like you to work on the questions first before I release the solutions and the solution videos. The idea really is not to memorize how to solve one problem, but to understand how to solve many of the problems. Okay, so I think I should stop it here.